Good day, this is Jim Pytel from Columbia Gorge Community College. This is Digital Electronics. This lecture is entitled Shift Register Applications. One of the first things that comes to your mind when I say shift register applications, you immediately should raise your hand and say memory. And the answer is yes, kind of. Okay, we'll go into an application of shift register in using a quote-unquote memory. In addition to that one application, there are other ways we could potentially use these devices. The first one of them is being a delay, is to generate a delay. Not all the time do you want your system signals arriving at the same time. Perhaps there is another combinational logic with an inherent delay and you want signals between two systems to arrive simultaneously. What we could do is purposely generate a delay, and how we do that is with a shift register. Consider the 4-bit shift register on the left hand side here. What I've got is the arrival of a D pulse at time whatever, and it's happening between a period of a fixed period of a clock. Okay, so there's a little bit of time, it's a portion of a period, which I'm going to call little t. Okay, so the arrival of that D pulse for that little time t, when does it show up in the Q0 input? Well, it shows up at the positive edge of that clock. So the Q0 output is delayed by a portion of a period, okay, which I'm calling little t. What is the Q1 output delayed? Well, it's a full period after Q0. What is Q2's output? Well, it's a full period after Q1, which is a full period after Q0, which is that plus that portion there. And ultimately, you get the picture here is, since the arrival of D input at that time, got a portion of a period plus 3 periods to get to a full Q3 delay. Okay, so I'm delaying it for 3 full periods and a portion of 1. So I'm delaying that. If I want that longer, what do? Just take an 8-bit shift register. And think what's happening here is the arrival of the Q0. I've got that portion of a period plus 7 periods. I can go ahead and adjust my clock frequency perhaps to go ahead and generate a longer delay. One other application for a shift register here is a waveform generator. For example, a Johnson counter. What I've got is a 4-bit Johnson counter, serial in, serial out, where that output is inverted and being fed back in, often known as a twisted ring counter. What does this generate? Well, it generates this staggered waveform for our outputs A, B, C, and D, which I've defined Q0 to Q3. What is this useful for? Perhaps these could serve as 4-bit input for a 4-bit combinational or sequential logic circuit. And what I can do is take that output and compare it with those known inputs to my expected outputs. If my expected outputs are matching my known inputs, chances are the thing is working. Be aware, however, the Johnson counter waveform here on the oscilloscope, look at those. I'm not really generating all possible combinations of input. And the deal is you don't necessarily need to test all possible combinations of input if you're doing what's called critical path testing. There are certain times that you have to realize, like think about 8-bit input, 16-bit input, 32-bit input. At a certain point, you are not going to be able to test all possible combinations of input. However, if you test certain critical paths that are testing out perhaps all routes within a circuit, you're going to go ahead and get those most problematic portions of a circuit troubleshot and verified before you say, hey, this thing's functional. Doesn't work all the time, but sometimes it is a cost-saving measure. You don't necessarily need to have all possible combinations of input. How can you do that? For a quick test, a Johnson counter or a twisted ring shift register. Obviously, serial to parallel and parallel to serial conversion is a great application of a shift register. Think about a serial in, i.e. 1 in, parallel out. What have you done? You've taken serial information and converted it to parallel. What about the opposite? Take parallel input, load it up. Once it's loaded, shift it out. What have I done? I've done parallel to serial conversion. Parallel to serial conversion, pretty easy. Serial to parallel, not so easy. The reason why is because you've got to have some agreed upon system to go ahead and send that data. It would be really hard to have this meaningless string of zeros and ones and go ahead and try to convert that meaningless string into parallel if you didn't know where to start. So let's go into some brief a system designed to do some serial and parallel conversion. We'll come back to this guy here in a little bit. Serial to parallel conversion. You have to have a known steady state. Basically, what I'm doing is I've got a input, and let's say if there's no data on it, it's going to stay constantly high. And I've got to have a start bit. Obviously, the steady state and the start bit should be different. So let's say that's a 0. What have I done here? All I've created is a known transition. In this particular case, it's a negative edge. You could do the opposite way. What have you created? It's a positive edge. For there to begin this serial to parallel conversion, you have to have this known transition. Additionally, you've got to know how long those individual bits are. Basically, what I'm saying is you have to have a known frequency. If you're operating a known frequency, each one of those positive or negative edges of the clock is going to generate what's called a bit time. What is the bit time? Well, it's the inverse of frequency. It's the period. A bit time, basically a bit has a certain time which it has the floor, okay? It is that period, and if you run this serial to parallel conversion at a faster or slower or basically incorrect frequency, you're gonna get the wrong answer. So you have to have a known frequency before you do this. Finally, last but not least, you have to have a known word length, okay? Are you using 8-bit words? Are you using 8-bit words with a parity bit? Are you using 8-bit words with a parity bit, MSB to LSB with a parity bit at the end? Are you using 8-bit words with a parity bit with LSB to MSB with a parity bit up front? So you've got to have these things agreed to before you even begin. So let's describe a simple serial to parallel conversion operation using some devices that we've already seen. The symbols right here should tell you what they are. This right here is a clock generator. It's got 2 pulses on it, whereas a single pulse on it, that's a one-shot. And what is this device up here? It's a D flip-flop. It's a negative edge triggered D flip-flop. When it is triggered, what does it do? The D input is always being held to 1. What's going to happen here is when it's triggered by a negative edge of the in, think about it, right there, it's going to set that D flip-flop. When it sets that D flip-flop, it's going to enable the clock. The clock is going to go at our known frequency, and it's going to enable this counter for a given word length. Okay? We've already figured out how we're going to do this thing here. So we've gotten our steady state transition, which starts it up. We go ahead and start the clock at a given frequency, and we count out, and for this particular case, it's an 8-bit word we're looking for. What does the other elements within this particular circuit do? What we've got here is a serial in, parallel out shift register. And as that data is being serially entered, it's being shifted in to its parallel outputs here. What is the device immediately below it? It is not a shift register. It is a parallel in, parallel out register. This is basically when this thing is done, this is the final answer. Okay, you'll see how that works here in a little bit. This counter, what is this here? It's the terminal count. It's the indication that this thing has reached its maximum sequence. Once it's reached its maximum sequence, what it's doing here, it's generating the terminal count and clock signal, signifying, hey, I've got my final answer, and clearing out these other devices to begin the sequence again. So now that I've talked about the basic circuit here, let's just talk about the timing diagram. Okay, so we've got a known steady state. We are assuming it is constantly a 1. So there's no data being set on it, no data being set on it. All of a sudden, we've got this negative edge transition, and our start bit is 0. It enables this D flip-flop, sets that D flip-flop, which enables that clock. The clock positive edge starts ticking. It clocks in D0 at this moment, D1 at that moment, D2 at that moment, so on, so forth. And what I'm trying to do is that D input could be whatever at those moments. That's when it's clocking it in. What is the count sequence at that positive edge? Well, it's gone from 0 to 1. Then it's gone from 1 to 2, 2 to 3, so on and so forth, at which point 6 to 7, it's reached the maximum of its count sequence. The terminal count goes high, and what we get is this brief moment in time where it's at 7, its terminal count is high, and the next positive clock edge comes along. What we get is this brief pulse, this positive edge. What happens? The final answer is transferred from the parallel in to the parallel outs of that register, because it's looking for a positive edge. At the same time, however, that counter recycles because it's modulus 8, it's reached the maximum, and that terminal count goes away, so it drops low. And what does that low negative edge do? It's a low negative edge which generates a one shot. It's taking from the negative Q inputs, the not Q inputs. So it's generating this low pulse. What does that low pulse do? Clears out the D flip-flop, resets the counter back to a state of 0. And the whole thing begins again. And if that input stays high, it's going to do nothing and wait for that next positive edge. So it's kind of this handshake that's done here. Okay, here's the things I need to know. I need to have a known steady state and a start bit. We're looking for a certain transition. Got to have a known frequency, which, by the way, is tangentially generating the bit time. I've got to have a known word length and orientation, MSB or LSB, and any of the other things that comes along with it. So let's go back to a serial to parallel and parallel to serial conversion. There's a device called the UART, and that does both of them. It does serial in to parallel out and parallel in to serial out. The UART stands for universal, i.e. serial in or parallel out or serial out. Asynchronous. Asynchronous means without respect to time. What it's implying is parallel and serial. Parallel is happening simultaneous and serial has a clock to it, so it's asynchronous. Receiver. It can receive and transmit. Universal, asynchronous, receiver, transmitter. And what the UART does is kind of serial to parallel and a parallel to serial conversion depending upon its mode. So what I can do is I can take parallel inputs and send it somewhere on a serial line. That same serial line, however, can be used as an input, and then the UART, what does it do? It takes it and converts it to a parallel out. And you may ask yourself, where does a UART typically show up? And it shows up on a bus. And your next question might be, what's a bus? Okay, so before we answer that question, what I want to do is talk about one of the final shift register applications, and that is memory in quotation marks. Thus far, I have been describing one of the major applications for a shift register is to perform the basis of memory. And notice, however, I'm putting it in quotation marks. It's kind of like memory. And a shift register to memory, if you could think about this, is a shift register is almost like one of those sticky notes that you use to remind yourself. Pick up your kid from gymnastics class. Pick up bread on the way home. You're giving yourself a temporary reminder. However, it's not designed for long-term storage. There are other logical applications, which we'll be discussing later on in this course, called memory. So this is a device called ROM memory. Here is a device called RAM memory. That's real memory. However, the interaction between that memory device, ROM or RAM, typically takes place between a bus. There's an intermediary, a register, in between the bus and that memory. And what it serves to act as is basically a temporary sticky note. The ROM can read from its memory, jot something on that sticky note. Now the bus has access to it. The UART could potentially take serial input, convert it to parallel, place it on the bus, and the bus will write to that sticky note on the register for the RAM memory. At which point the RAM memory, if it wants to write the contents of that memory to itself, it can just take the contents of that sticky note. In reality, these registers that we've thus far been describing are kind of temporary interactions between true memory and, in this case, a bus. We are kind of transitioning to the end of the shift register lectures and going on to some more advanced topics here. And what I'm not intending to do is I am not intending to make this a computer science course or a microprocessor design course. There's several reasons for that. Number one reason why, because by the time I even write the contents for this lecture, it will be immediately outdated, okay, because the design of these things are happening so fast. So chances are we're going to do a lot more current applications as opposed to some of the online lectures. I do, however, want to talk about some very basic concepts, and right now just go ahead and look at this from the perspective of a register application. Okay, a bus. Let's go ahead and answer what the bus is. The bus, if you can imagine, it's like the world's worst highway, because only one thing can be going on it, one direction. So if there is a car on it, think of the highway analogy, it's going in one direction. And if there wants to be another car on that highway, it's got to wait till the first car gets off. And then that first car gets off, then the second car can get on and can get go its direction. And that's kind of what's known as source and accept. There can be only one source. Basically, I've got a couple block diagrams here. I've got a microprocessor, I've got a ROM memory, a RAM memory, and devices A, B, C, and D. And then I've got our UART. The UART basically acts as an interface between this computer system and potentially another computer system via a single serial line. And that's the purpose of the UART. It's taking that serial in, it's converting it to parallel out, and placing it on the bus if it wants to receive data. However, if it wants to send data from this particular computer system, it's taking parallel in, converting it to serial out, and sending it to something else. The source, there can be only one source. Let's say, for example, the UART wants to talk to device A. The UART is the source. Device A is the acceptor. I can have several acceptors, be aware, because the UART could send to A and to B. What's it sending to? It's basically sending to A's and B's registers, interfacing with that bus. I've drawn only one bus in the system, but be aware, and I've been describing kind of a data bus. Be aware that there are several buses within a microprocessor or computer system here. There's a data bus, i.e. the data. Let's say we're trying to send the number 50101. That's the data. The control bus, basically that is the interaction between who is talking. The UART is talking to device A and to B and some of those other control signals. And additionally realize there is an address bus, especially with the interaction between the ROM and the RAM memories, because there is data stored in those memories. And if you could think about a city, there is avenues and streets in pretty much every city on earth except for Salt Lake City, but they've got their own weird problems far beyond their street system. It's an address. It's the avenues and streets. That's the address. Okay, where is that data? Okay, so there's an address. What's the data? It's the contents of the building at that streets and streets and avenues. Okay, that's the address. So realize there are 3 buses, sometimes more, typically control the data, the control, and the address buses. Okay, so obviously with one source, you want to kind of avoid a conflict. Okay, what that conflict is called contention. That's when you have more than one source. That's not a good idea. 2 things are trying to talk on this world's worst highway. 2 cars running into each other. Not a good idea. It's not going to work. So how you do that is called arbitration. That's one of those, and think about the term arbiter. It decides who has priority over it. Sometimes the microprocessor, that's called synchronous bus control. This guy being the microprocessor right here, it is originating bus control and it decides the arbitration. Whereas there is something called asynchronous bus control, where there's a source and acceptor handshake, basically freeing the microprocessor to do something else. So basically, UART and A do a handshake, letting the microprocessor, look up pictures of cats on the internet, doing something far more important. So if this is the case, where we want only one source, and you've got to make sure that the acceptor, the correct acceptor is doing that, what is the interface with this bus? It's typically a register. So this is our registers here, and this example is a 4-bit register. How do you connect and disconnect these things? Well, you use this device. It's called a tri-state buffer, and basically based upon the contents of the control bus, it will either connect or disconnect your source or acceptor. And what a tri-state buffer is, think about here, is there is an input here and an output here, and there's an enable signal on it. It's almost like an inverter, but there's no bubble on it, so it's not inverting it. What that enable signal on a buffer does, all it is, it's a switch. When, in this particular case, since there's no bar over it, when there's a 1 on enable, what's that switch do? It closes, and it connects something to that bus. I can have, basically, these are non-inverting buffers, and the fact that they are not inverting that input to the output. I could potentially have over here on the right-hand side an input, and I can have an inverting output and a not inverted output. So sometimes you'll see symbols like that. It's still a tri-state buffer, but realize that there's an inverting output and a non-inverting output. And again, it connects it or disconnect it based off that enable. You want to active low enable, that's what that symbol looks like. It's a buffer with a bubble on the bottom, and when that enable has a 0, it connects it. Why is it called a tri-state? The reason why it's called a tri-state is because if in's a 1 and it's closed, out's a 1. If in's a 0, and we're talking about non-inverting buffers, in's a 0 and it's closed, the output's a 0. However, what is the third state when it's not enabled? It's called Z, high impedance. What's high impedance? An open switch. Okay, infinite resistance. Really, all it is a switch. So now what I've got here is I've got these back-to-back configuration of tri-state buffers. The ones with the bubble on them are going to close when that red line right here has a 0 on it. The ones without the bubble on it will close when that red line has a 1 on it. Okay, and so look at what we've got here. This thing can basically act as an input and an output to what's that thing on the right hand side supposed to represent. It's 4 lines trying to represent the bus. What is this particular device? This is perhaps the RAM memory's register. This is the 4-bit data that finally was retrieved from that true memory. It is stored in this 4-bit register. Now we go ahead and go into output mode. What is output mode? Basically, send. Look at the not S signal. I send a 0 to that red input line. Which tri-state buffers are connected? These guys. It's sending to the bus, and now that particular device, that particular data goes to whatever, and now we get another control signal. Okay, I want to write to RAM. What happens? The receive command is asserted, and now that previous input to the bus is now becoming, let's describe it this way. It was inputting to the bus, now it's taking from the bus. It's receiving from the bus. And now it's taking the contents of that bus and placing them in a parallel into this particular parallel in register, and then the RAM memory can perhaps do a write command. Let's say this is a new piece of data that we want to store in true memory. I can go ahead and retrieve the contents of that register. The long and short of it, the shift register application is basically, it's an interface. It's a temporary storage of data, typically interacting with a bus. Okay, it's not meant for long-term storage. However, it's still memory. This by no means concludes shift register applications. There are a number of different applications, but these are the most prominent ones. And like I said, the interaction between the bus here is basically you need to potentially store 2 operators. For example, add number A and B for an arithmetic unit. You want to basically use the bus to store A, perhaps from memory, store B, perhaps from another place in memory. Go ahead and perform this operation on it, at which point this can output the number C, which is the A plus B, and then it can be sent onto the bus to another device which might need that. Every single interaction between that bus is interfaced with registers. So let's go ahead and complete our shift register unit here with a description of shift registers using VHDL.